Every alkyl halide molecule harbors a microscopic tension. A highly electronegative halogen atom pulls electrons toward itself, polarizing the bond and leaving the adjacent carbon exposed. This electron-starved carbon acts as an electrophile. It attracts electron-rich nucleophiles and bases, setting the stage for a chemical collision. When an attacker strikes, the system forces a choice. The incoming molecule will either replace the halogen in a substitution reaction or remove a neighboring hydrogen to form a double bond through elimination. The strength and physical size of the attacker determine which pathway is more favorable. Predicting the outcome of this microscopic clash allows chemists to manage yields in large-scale pharmaceutical production, ensuring the reaction produces the intended compound rather than a useless byproduct. With a strong nucleophile, the attacker strikes the carbon directly from the opposite side, executing a backside attack. This physical docking forces the molecule's bonds to bend backward. This Walden inversion flips the spatial arrangement of the atoms, like an umbrella blowing inside out. If we swap that nucleophile for a bulky base, like tert butoxide, the carbon center is physically blocked. The attacker cannot reach the electrophilic target. This physical blockade shifts the yield toward E2 elimination. As seen in this 85% result for the hindered base, the attacker is forced to grab an exposed peripheral hydrogen instead. For a double bond to form, the hydrogen and leaving halogen must be locked on opposite sides of the molecule's plane in an anti-periplanar alignment. In these single-step reactions, physical bulk and 3D geometry override raw electrical attraction to determine whether the pathway ends in substitution or elimination. When the carbon target is heavily shielded or the attacker is weak, the reaction relies on the halogen breaking off on its own. This diagram highlights the intermediate phase. The center reveals a planar carbocation intermediate, a flat structure bearing a positive charge. Because it is flat, the nucleophile can attack from either side. This destroys original 3D purity, leaving a racemic mixture of both configurations. Alternatively, the carbocation can stabilize itself by shedding a neighboring hydrogen, folding the leftover electrons inward to form a double bond via the E1 pathway. These reactions prioritize neutralizing the unstable intermediate. Because multiple outcomes are energetically similar, the process often yields a mixture of different products. A primary or secondary carbocation positioned next to a tertiary carbon is energetically unfavorable. The system is too unstable to wait for an external attacker. As shown in the blue annotation, the neighboring electron cloud migrates. The empty orbital pulls a methyl group over to the positively charged site. The pentocolone product reveals a rearranged carbon skeleton. The positive charge has moved to a more stable position. This shift demonstrates how a molecule will spontaneously reorganize its internal architecture to reach a more stable state. Synthetic strategy involves manipulating environmental variables to favor one reaction pathway over another. Higher temperatures increase the kinetic energy of the system, which selectively favors the higher entropy of elimination reactions. This mechanism review table compares how choosing specific solvents, like polar A product versus protic, either activates or suppresses the nucleophile. The structure of the target molecule also provides a guide. Simple primary carbons favor substitution, while crowded tertiary carbons favor elimination and unstable intermediates. These pathways demonstrate how specific geometric and thermodynamic constraints allow for the predictable construction of complex organic molecules.